Superconductors. Hello and welcome to this video on superconductors. Superconductivity is a fascinating phenomenon where certain materials exhibit zero electrical resistance and expel magnetic fields. This property has a wide range of practical applications, from medical imaging to power generation, and has the potential to revolutionize the world of electronics and computing. In this video, we'll be discussing everything you need to know about superconductors, from their history to their uses, and the current state of research in the field of superconductivity. Definition of superconductor. A superconductor is a material that exhibits zero electrical resistance and perfect diamagnetism at or below a certain temperature, called the critical temperature, Tc. This means that when a current flows through a superconductor, there is no energy loss due to resistance, and that a magnetic field cannot penetrate its interior. This property is known as superconductivity, and it allows for the creation of extremely powerful electromagnets, efficient power transmission lines, and other important technologies. Superconductors are typically made from metals, metal alloys, or certain ceramics, and require extremely low temperatures to exhibit their superconducting properties. History of superconductors. The phenomenon of superconductivity was first observed in 1911 by the Dutch physicist Heike Kamerlingh Onnes. He discovered that at very low temperatures, mercury and some other metals and alloys suddenly lost all electrical resistance. This discovery opened the door to a new field of research, and scientists began to study the properties of superconductors in detail. In the 1950s, researchers discovered that the critical temperature at which superconductivity occurs could be increased by adding impurities to the material. This led to the development of the first practical superconducting materials, which were used in applications such as magnets for medical imaging and particle accelerators. In the 1980s, a breakthrough discovery was made by researchers at IBM and the University of Houston. They discovered a new class of high-temperature superconductors, which could exhibit superconductivity at temperatures above the boiling point of liquid nitrogen. This discovery opened up new possibilities for practical applications of superconductivity, and research in the field has continued to grow ever since. Types of superconductors. There are two main types of superconductors, Type 1 and Type 2. Type 1 superconductors are metals that exhibit superconductivity at very low temperatures, typically below 10 K, and they expel magnetic fields completely. They have a single critical magnetic field, above which they become normal conductors. Type 2 superconductors, on the other hand, are materials that exhibit superconductivity at higher temperatures, up to 135 K, and can tolerate higher magnetic fields. They have two critical magnetic fields: the lower critical field, where they start to allow magnetic flux to penetrate, and the upper critical field, where superconductivity is completely destroyed. Applications of superconductors. Superconductors have a wide range of applications in various fields, including medical imaging, transportation, power generation, and computing. In medical imaging, superconducting magnets are used in MRI machines to produce detailed images of the human body. These magnets are typically made of Type 2 superconductors, which can tolerate the strong magnetic fields required for MRI imaging. In transportation, superconducting magnets are used in maglev trains, which use magnetic levitation to reduce friction and increase speed. These trains can travel at speeds of up to 600 km per hour, and have the potential to revolutionize transportation in the future. In power generation, superconducting cables are used to transmit electricity with minimal loss of energy. These cables are made of Type 2 superconductors and are used to transmit electricity over long distances, reducing energy loss and increasing efficiency. In computing, superconducting materials are being developed for use in quantum computers. These computers use quantum bits, qubits, instead of traditional bits, and require materials that can operate at very low temperatures and exhibit zero electrical resistance. Current state of research. Superconductors have been a topic of research for over a century, and the field is still very active today. Some of the current areas of research in superconductivity include high-temperature superconductivity. Researchers are trying to discover new materials that exhibit superconductivity at higher temperatures, which would make superconductors more practical for real-world applications. Understanding the mechanism of superconductivity. Despite decades of research, there is still much to be learned about the underlying mechanism of superconductivity. Scientists are studying the behavior of superconducting materials at the atomic level in order to gain a better understanding of how they work. Applications of superconductors. Superconductors have many potential applications, including in power generation, medical imaging, and transportation. Researchers are working to develop new technologies that can take advantage of the unique properties of superconductors. Novel superconducting materials. New materials with superconducting properties are constantly being discovered and synthesized. Researchers are exploring the properties of these materials and their potential applications. Overall, the field of superconductivity research is very active, and there is still much to be learned and discovered about these fascinating materials. Developing superconductors for daily use, challenges and limitations. Despite the potential benefits of superconductors, there are still several challenges and limitations that need to be addressed before they can become practical for daily use. One major challenge is the cost of producing superconducting materials. The materials used in superconductors are typically expensive and difficult to manufacture, which makes them unsuitable for widespread use in consumer electronics and other applications. Another challenge is the need for extremely low temperatures to maintain superconductivity. Most superconductors require temperatures close to absolute zero, -273 degrees Celsius, to exhibit zero electrical resistance, which makes them impractical for use in everyday applications. Additionally, superconducting materials are often brittle and difficult to work with, which makes them challenging to incorporate into practical devices. This has limited their use to specialized applications such as MRI machines and particle accelerators. Another limitation is the issue of magnetic fields. While superconductors can expel magnetic fields, they are still affected by external magnetic fields, which can interfere with their performance. This makes it difficult to use superconductors in applications where strong magnetic fields are present, such as in motors and generators. Furthermore, the behavior of superconductors can be complex and difficult to predict. Researchers are still working to understand the mechanisms behind superconductivity and to develop new materials with better properties and performance. Despite these challenges and limitations, research in the field of superconductivity continues to progress. New materials and technologies are being developed that could make superconductors more practical for everyday use. One promising area of research is the development of high-temperature superconductors. These materials exhibit superconductivity at temperatures above the boiling point of liquid nitrogen, which would make them easier and more cost-effective to maintain. Another area of research is the development of flexible and lightweight superconductors that can be integrated into practical devices. Researchers are exploring new manufacturing techniques and materials that could make superconductors more durable and easier to work with. Finally, research is also being conducted into new applications of superconductors. For example, superconducting magnetic energy storage (SMES) systems could be used to store energy from renewable sources such as wind and solar power. This could help address the issue of intermittency in renewable energy and provide a more stable and reliable source of electricity. Conclusion. In conclusion, superconductors are a fascinating and promising area of research that has the potential to revolutionize a wide range of applications, from healthcare to energy generation. Despite the challenges and limitations that exist, researchers are working to develop new materials and technologies that could make superconductors more practical for everyday use. The development of high-temperature superconductors and flexible, lightweight superconductors are promising areas of research that could make superconductors more practical for consumer electronics and other applications. Additionally, the development of new applications such as SMES systems could help address some of the major challenges facing the energy industry. Overall, superconductivity is a field that is constantly evolving, and researchers are working to push the boundaries of what is possible in this exciting field. We look forward to seeing how superconductors continue to develop and improve in the coming years, and to the many exciting new applications that they will enable. As we conclude this video, we hope that you have gained a deeper understanding of the challenges and potential of superconductors, and the incredible impact they could have on our world. With ongoing research and development, we may soon see a future where superconductors are a practical and everyday part of our lives, revolutionizing the way we generate and use energy, and improving countless other technologies. Thank you for watching.